next lesson in acids and alkalis. To start with, there are 4 questions for you to do as a knowledge retrieval. So if you pause the video and give yourself at least 4 minutes to have a go at these. So here are the answers from that knowledge retrieval. So main one, which I think might have been trickier, was explaining what the difference was between concentrated and dilute. So talking about the number of particles. Now here I've used specific keywords, so solute and solvent. So solute is the substance which is dissolved in another substance, being the solvent. So our acid solute particles get dissolved in water as our solvent particles. So it's a mixture between those acid particles and the water particles. So in concentrated solutions, we have high numbers of those solute particles compared to dilute. So if we compare equal volumes of concentrated and dilute solutions, the concentrated have more of those particles. We looked last lesson at squash and we saw how we could see the colour difference between a concentrated and dilute solution. So that's really helpful for coloured solutions, but obviously it's not always possible with our acids and alkalis because they tend to be colourless. So before we begin today's lesson, I'd like you to consider these different views about whether caustic soda, which is used as a drain cleaner, is an acid or an alkali. So just pause the video, take some time to read through the statements and have a think about which statement you most agree with. You may agree with lots of them, you may agree with none of them. So take your time, read through them whilst you pause the video. Okay, so going to talk through what some of these people are thinking. So Angelica said it must be an acid because it can eat away blockages. So this is referring to the fact that it can react with the substances that are causing blockages, and due to its corrosive nature, those blockages then go away. However, as we looked at last lesson, we saw that both acids and alkalis are corrosive. So the fact that it eats away blockages is not enough for us to determine whether it's an acid or an alkali. Similarly, Freddie, now he's used that key word of corrosive, that warning label that we put on both acids and alkalis. But again, just the fact that it's corrosive doesn't tell us whether it's an acid or an alkali. Sam said he thinks it's an alkali because it is a type of cleaning product. Now, we said last lesson that a lot of alkalis, they do tend to be cleaning products. However, I did also say that it's not a rule that all cleaning products are alkalis or that all alkalis are cleaning products. It just is part of a pattern that a lot of cleaning products are alkalis. And then Dexter has said, I think it is an acid because acids are stronger than alkalis. Now, we haven't really talked about strength of acids and alkalis, but we have looked at both industrial and everyday, both acids and alkalis. And from looking at those, we can see that there are strong acids and alkalis that we use industrially, but also weak acids and weak alkalis that we use more every day. And that are safe to consume. Claudia says that she can't tell whether it is an acid or alkali. I need more information. So Claudia is probably the person who I would agree most with, because none of these statements or none of the information that we've been given is enough to determine whether it's an acid or an alkali. So this brings us on to our focus of this lesson, looking at how we can tell if something is acidic or alkali. So today we're going to be looking at pH scale and indicators. Now I've prepared a worksheet to accompany this video to try and guide your notes so that you're writing down everything that you should. There are some bits that aren't included on the worksheet that you will need to be writing in your book, but hopefully it becomes clear which bits should and shouldn't be written in the worksheet. Okay, so we're going to kick off with indicators. So these are solutions of compounds, and the special thing about indicators is that these solutions are coloured, but importantly they have different colours in acidic solutions to alkali solutions. So if you can write that definition in your worksheet, please. And we're going to look at a couple indicators in this lesson, but I'm also going to ask you to, obviously with your parents' permission, have a go at making your own indicator using red cabbage. So the Royal Society of Chemistry has prepared a video to show you how to do this. I would suggest having an adult supervision because of the need to cut up the red cabbage using a knife, and also the need for the hot water in order to extract the indicator from the red cabbage. But we'll come to that a bit later on. So the first one we're going to look at is litmus paper. Now there are two types of litmus paper, red litmus and blue litmus. So in your worksheet you have a table which we're going to fill in by watching a video.
Diluted in water. We have lemon juice, which has also been slightly diluted in water. And speaking of water, here is water. So when we're testing these liquids, we need to use both the red and the blue litmus paper, as you can see over here. And the reason for that is the following. When you put blue litmus paper into the base and you pull it out, the blue litmus paper remains blue. So I was thinking of it as the 3 Bs. Blue, base, blue. Does it make any sense? The blue remained blue, therefore it is a base. Hope that makes sense. When you put the red litmus paper in and you pull it out, the red litmus paper turns blue as well. Remember, blue base. And therefore we can tell that bicarbonate of soda is in fact a base. Moving on to lemon juice. If I take the red litmus paper and put it into the lemon juice, which we know is an acid, we can see that the red litmus paper remains red, therefore it is an acid. However, if we put the blue litmus paper in, and remember the blue remained blue in a base, this time the blue litmus paper goes red, which indicates that the lemon juice here is indeed an acid. But the fun part comes when you get to water. When you take red litmus paper and put it in water, it remains red. And when you put blue litmus paper in water, it remains blue. So what does that mean? I would like you to think about that, and you can let me know either in the comments below or in your
Okay, so as we were watching the video, hopefully we saw that with our bicarbonate of soda, which he was referring to as something called a base, and we'll talk about the relationship between bases and alkalis in a later lesson, but for the purposes of this, it is an alkali solution. So with our base, our red litmus paper turned blue, so red changed to blue, whereas our blue litmus paper, and he kept reinforcing that idea, blue base blue, so that blue litmus paper remained blue, whereas our lemon juice, which is an acid, our red litmus paper remained red, and our blue litmus paper went from being blue to being red. our water, this is an example of something which is neutral, so it is neither acidic nor alkali. And here our red litmus remained red, and our blue litmus remained blue. So now in your worksheet, I would like you to consider what happened to the red litmus paper and what happened to the blue litmus paper. So pause the video, write down on your worksheet what happened to the red litmus paper in acids, what happened to it in alkali, and what happened to it in neutral, and similarly for the blue. So just pause the video whilst you do that. And now you have a couple questions to answer on your worksheet. So pause the video whilst you consider firstly what the solution in the test tube must be if a red litmus paper turns blue, and then filling in a confidence grid for that one part B as to which of those solutions you think could be in that solution, and think about how confident you are in your answer. So selecting one column for each of those solutions as to whether you think it's right or wrong, and whether you're sure it is or whether you just think it is. So pause the video whilst you do that. Okay, so the next indicator we're going to look at is universal indicator. Now, universal typically means it's suitable for all. And what you can see here is that it has a range of colours from red through to purple. So this universal indicator has a gradual colour change through a spectrum of colours, and this covers a wide range of pHs, and we're going to talk about what pH means in a minute. So on your worksheet there is a rainbow scale. We're going to come on to that in a moment, but just wanted to draw your attention again to the home experiment that you can do to make your own indicator, so red cabbage indicator, so that you can test some of those everyday acids and alkalis that you have in your home. So this is similar to what you have on your sheet. So at the top it shows us those regions between acid, neutral and alkali. And universal indicators and litmus paper indicators, they go quite nicely, because in both of those indicators the acids are red and the alkalis are blue, with universal going more into that purple region at those higher pHs. But the advantage of our universal indicator is that it has that change through different pHs, and so we can use that to identify the different concentration and strengths of alkalis and bases, with our neutral also being picked up as a colour. So what we've got underneath that bar is some examples of different substances which you may or may not have come across, some of which we talked about in our previous lessons, such as vinegar. We talked about indigestion tablets and baking soda. We talked about soap, and we talked about bleach. So here you can see that even though we have that division between acids and alkalis, it's not quite clear cut as that. There is a spectrum from acids through to alkalis, and universal indicator allows us to see that. So from that grid, you will have seen that those acidic solutions all have a pH of less than 7. So I'm hoping we're familiar with this mathematical symbol here. That means less than whilst this symbol means greater than. So our alkalis have a pH above 7, our acidic pH is less than 7, and our neutral have a pH bang smack in the middle at 7. So we typically refer to our acidic solutions as having low pHs because they're towards the lower numerical numbers such as 0 and 1, whereas our alkali solutions, they have a high pH. So if you just pause your video and fill in the necessary parts on your worksheet. Okay, so we've got another discussion here about what is distinctive about an acid. So pause the video, take some time to read their statements, decide who you agree with, why you agree with them, and how you could safely find out whether a solution is an acid. So hopefully we have decided that Phil is correct because blue litmus would turn red, whereas red litmus would remain red. If we're talking about blue litmus, that would turn. We do not say that acids melt metals, we say acids corrode metals. So remember, corrosion is a chemical reaction, whereas melting is a physical change. So with melting, you're not actually changing the substance, whereas with corrosion, we are reacting the acid of the metal, and so we do get different substances. So acids do not melt metals, they react with them, they corrode them. Similarly, Jerry has not used proper scientific terminology. Acids don't eat materials away. Acids are not living organisms, they do not eat. They react with materials and corrode them. Molly has said acids burn you. So here we want to distinguish between chemical burns and burns as a result of heat. So acids, they can react with your skin, corrode, but it isn't a burn as a result of heat. And then Alicia said vinegar is an acid, so some acids can be eaten safely. And here Alicia is correct. Some of our everyday acids can be consumed easily. And remember, if we think back to a few slides ago when we were looking at the universal indicator, one thing I didn't highlight but you might have spotted is that actually our stomach is full of acid, and that is at a pH of 1. So our body is quite good at dealing with our everyday acids. It has something that is more acidic within it. So we're now going to talk about the pH scale, because I've been using this term pH. We've talked about where our acids and alkalis lie on our scale, but we haven't actually talked about what this scale is. So the pH scale measures the acidity or the alkalinity of a solution using a number, often between 1 and 14. So the pH scale is a logarithmic scale. Now, other logarithmic scales you might have come across is the Richter scale. And this is used to measure earthquakes. And with the Richter scale, I think it goes from about 0 to 7 or 9 perhaps. But as you go 0, 1, 2, 3, etc., you are saying that that earthquake is 10 times as bad as that one. So it gets worse as you go to the higher numbers. So you're talking about the most severe earthquakes at that higher number. With our pH scale, we actually go in either direction. So starting off at our neutral position, going left, we go into our acidic region, because we're going into an area where our pH is less than 7. And as we go from 7 to 1, we are getting more acidic. So this is our most acidic, is down at our 1 and 0 end. So what we're saying here is that a pH of 4 is 10 times the acidity of a solution that is pH 5. If we though look at pH 3 compared to pH 5, we've had to do a double jump here. And we can combine these two, so times 10 times 10, 10 times 10 is 100. So that pH solution of 3 is 100 times the acidity of a pH of 5. And similarly, we can go in the other direction for our alkaline solutions, which have a pH greater than 7. And we're getting more alkali as we go down, with our most alkaline being at that pH of 14. And again, we can compare pHs. So here if we compare pH 10 to say pH 14, we are having to go 1 jump to 11, 2 jump to 12, 3 jump to 13, 4 jump to 14. Got 4 jumps, so that's 10 times 10 times 10 times 10. 10 times 10 is 100, times 10 is 1,000, times another 10 is going to be 10,000. So therefore pH of 14 is 10,000 times the pH of a solution of 10. So 10,000 times more alkaline than our pH solution of 10. So question for you to consider. So pause the video, have a read through the different options, think about what we just went through on the previous slide. So here we're looking at the comparison between 1 and 2. So remember, 1 is our most acidic. We're moving away from neutral, so we're moving in this direction. It's only one number away, so it's just 1 times 10 that we have to do. So our solution Y, which is a pH of 1, is 10 times the acidity of X. So looking at our options, it's therefore got to be C, because it's 10 times on that logarithmic scale. So with our logarithmic scale, we are moving up by a power of 10, so 10 lots of it, rather than just adding 1. We're moving times 10. So 4 questions for you to have a go at. There's not space on your worksheet, however you can do it on the back or in your book. So pause the video whilst you have a go at these, and then just leaving you there with that link for the RSC's Red Cabbage Rainbow Experiment, which I hope many of you will complete as your homework over the next week. Thank you all for watching. I hope it was helpful. As always, please do get in touch if you have any questions or problems. I'm going to try and have a go at this experiment myself over the weekend. May not be with red cabbage, maybe with red onion instead, as that's what I have in my food cupboard at the moment, but we'll see how my food shops do over the week. But do send me an email, message me on Teams if you have any problems, and I will see you all for our next lesson. Thank you very much.